analysis topics for doing some calculations, doing dimensional analysis, and I'm sure anybody who's seen the topic of significant figures or significant digits in high school, I'm sure you're really excited to see that topic again. If you haven't seen it before, I'm sure you can't wait to get into that topic. Okay, so the topic itself of significant figures is going to be how we start rounding problems and knowing where to round the results of problems that involve some sort of laboratory measurements or values that we're assuming are based on laboratory measurements. Okay, so a couple of things that we were talking about last time, we're getting into metric prefixes. We're using like the gram to, or the joule to kilojoule conversion. So using that kilo prefix. Which ones of those prefixes do you need to know? Those ones are kind of shown here, and we'll go over them in just a second. So giga, mega, kilo on the bigger side of our units. And then on the smaller side, centi, milli, micro, nano, and pico. And if you forget what these units are referring to, and let me do something real quick on my end, just so. I get a computer here, I just wanted to show the display if I can. All right, well, that's not changing. Anyways, so the prefix giga is 10 to the 9. If we go through mega, 10 to the 6, and then kilo, 10 to the 3. And so the way this would work is if you had that unit, so say you had kilograms, so 1 kilogram is equal to 10 to the 3 grams. And if you had a megagram, that would be 10 to the 6 grams. And then obviously the giga prefix, so 1 gigagram, capital G, little g, would be 10 to the 9 grams. So we're going to want to know how to use those prefixes if they come up in problems throughout the course. And then on the smaller side, we have centi, that's 10 to the minus 2, 10 to the minus 3 for milli, and then 10 to the minus 6, minus 9, and minus 12 for nano and pico. It's been a while since I've seen pico used in problems. It's one every semester. I kind of wonder if we should just exclude from the list of prefixes just to kind of know through doing a couple examples or through just trying to memorize pico, 10 to the minus 12. But you'll see nano a lot. When we get into chapter 6, we'll use like nanometers as a common unit. And we'll want to make sure that we know that if we're converting, say, nanometers, 1 nanometer is really small. So 1 nanometer is 10 to the minus 9 meters. 1 micrometer, that's the Greek symbol mu. For micrometer, would be 10 to the minus 6 meters, etc. So we're just going to know how to use these metric prefixes and know those ones so we can use them in problems. We want to know the basic SI units for a couple different quantities, like length, mass, quantity, temperature, and time. These are what we call the base SI units, for which there's a carefully defined unit in the SI system that defines this unit. So for length, the unit's the meter. For mass, it's the kilogram. Kind of interesting that the SI unit of mass wouldn't be just the gram, but it's the kilogram. So we got that prefix out in front. Quantity is the mole. You might not remember too much about the mole. We'll talk about that in chapter 3 and go into detail about mole units. You might remember that it's an Avogadro's number of particles, represents the mole unit. Temperature, the SI unit is the Kelvin scale. Kelvin maybe isn't the most commonly used temperature scale that you've used before. Maybe you've never even seen it before. We'll talk about conversions for temperature units in just a second. We use Celsius, obviously, and I'm sure you're familiar with that scale. But then Kelvin's used in a lot of problems, especially when we get to chapter 10. Almost every problem we do in chapter 10 will require the use of the Kelvin scale. And then time is just seconds. So those are 5 of the 7 base SI units. There's 2 units. Luminous intensity is the candela, and then electrical current being the amp, are 2 other base SI units that don't come into play too much in Chem 1210. So there are 2 other base SI units, and those 7 units are somehow embedded into any other more complicated SI unit. Like last time we were talking about the SI unit of energy being the joule, which is defined as the SI unit of energy based off of these fundamental units. So whenever you have a non-fundamental or a non-base SI unit, it has some definition based on those base SI units. So that's the whole idea of why do we have base SI units? They serve as the foundation for all the other SI units, like energy. We saw last time 1 kilogram meter squared per second squared. Now, this particular relationship or that conversion factor for joules into kilogram meter squared per second squared, nothing, I wouldn't memorize this. So I wouldn't memorize that equation there. That's not something you're going to have committed to memory. The metric prefixes I would have committed to memory, just so you can convert kilograms, micrograms, milligrams, et cetera, as necessary. And then I would know the base SI units. I don't know why we ask questions, but sometimes you'll see a question, you'll see some on some of the practice quizzes like, what is the base SI unit of mass? And the answer is kilogram, as opposed to grams or milligrams or some other unit. Then our temperature conversions, and these I think we're going to go over an example in just a minute, just to kind of make sure we're on the same scale of thinking about temperatures and the scale of Celsius, and then being familiar with converting them into Kelvin units. And so then our temperature, I don't know why that just made everything blurry when I erased, but anyways, our temperature in degrees C, we can calculate that off of a temperature in Fahrenheit by the equation here. Now this equation isn't necessarily one that I would memorize either. If you have to do a temperature conversion on a test, we'll give you these equations. So if you need to calculate or convert between Fahrenheit and Celsius, we're not going to expect that you have these equations memorized. But to calculate a temperature in degrees C, we take 5/9 times the quantity of the Fahrenheit temperature minus 32. If we need to go to Fahrenheit, we just do the arithmetic to solve for the temperature in Fahrenheit. So that ends up being 9/5 times the degree C temperature plus 32. And then the big one, and this is, if you haven't seen the temperature in Kelvin scale, it's an absolute scale. So meaning temperatures can't go below 0 Kelvin, the lowest possible temperature would be 0. In the Celsius scale, you can go all the way down to minus 273.15 Kelvin. And so that's our conversion factor over to Kelvin. We take our temperature in Celsius and we add 273.15 to the temperature. So if you're talking room temperature, I think we all know that's about 25 degrees C. So we add 273.15, we get 298.15. So we can easily just add 273.15 to do the exact conversion. So 25.00 degrees C would end up being 298.15 Kelvin. And for whatever reason, we don't put degrees Kelvin, we just put Kelvin. So we don't put the little degree sign for the unit of Kelvin. And so then we have the derived SI units of energy, like the joule for energy, which we previously talked about. We have SI units for volume, like the liter. Actually, the SI unit of volume would be the cubic meter. Because if you define volume off the base SI unit, you go 1 meter times 1 meter times 1 meter. So your base unit of volume would be cubic meters. And then you could relate that to the unit of liters, that this is going to be equal to 1,000 liters. So 1,000 liters are defined as being equal to a cubic meter. So if you had a cubic meter by cubic meter by cubic meter, that's a pretty big box. You're going to fit 1,000 liters inside of that box. And then density, there's a few different kind of base SI units for density. The kind of obvious one would be kilograms per cubic meters, right? Because we're just kind of taking our base SI unit of mass, our base SI unit of volume, cubic meters. And so this is just a mass divided by a unit volume. So our main SI units would be kilograms per cubic meter. But you also see, obviously, grams per milliliter used a lot for this unit. And there are some conversion problems, maybe we'll look at those a little bit later, on converting a density in like grams per milliliter into kilograms per cubic meter. But let's come back to that kind of thought later on how we can convert to and from different density units. And then we'll get into some temperature conversions. Then after that, okay, so let's again kind of inspect this temperature scale. One thing I think it's nice is just to look at a thermometer at the melting point of water and the boiling point of water in our two kind of more commonly used temperature scales, 0 to 100 in Celsius. If you've never seen Fahrenheit before, it's 32 and 212 Fahrenheit. So that's the range of the melting point and boiling point of water. So about 100 degrees C, a little less than 200 degrees Fahrenheit separating the scale. And then if you're just adding 273, to 0 and 100, you get 273 to 373 Kelvin. So notice that you get 100 Kelvin increase in temperature between the melting point and boiling point of water, just like you have a 100-degree increase in temperature in the Celsius scale. So Kelvin and Celsius kind of go hand in hand. If you go up by 1 degree Celsius, if you go from 25 to 26 degrees C, you go from 298 to 299 Kelvin. When we get to chapter 5, it's going to be helpful when we start thinking of changes in temperature, that if you change your temperature, degrees C and Kelvin are actually the same. So if you go up by 5 degrees Celsius, the temperature would have gone up by 5 Kelvin. So that's just a thought to have in the back of our minds, that when we start looking at problems in chapter 5, we're going to see some similarities between temperatures in degrees C and Kelvin. You may think that or we're missing a conversion factor, but a difference in temperature, if you go up by a degree, you go up by the same temperature in both scales. So I just wanted to point out that similarity between Celsius and Kelvin. Is when we start getting into some significant figures and doing some of those conversions. Okay, so have a great weekend. Next Monday, we'll be talking about a lot of different math topics that relate to rounding and all that fun stuff. Have a great weekend. Okay, there's actually a little typo on this slide. But we want to convert 98.6 degrees Fahrenheit to Celsius and to Kelvin. You can use the previous slide that has the equations. Like if we had to do this on a quiz, or we don't have graded quizzes, but if we had a test that asked this question, we would give you the equations either on the front of the test on the equation sheet or within the problem somewhere, so you didn't have to have those equations memorized. So when I take 2 or 3 minutes, let you guys just go through the calculation into Celsius and the calculation into Kelvin for 98.6 degrees Fahrenheit. So take a couple minutes here. Feel free to talk amongst yourselves or try it first for a minute and then double check if you wish. So I think we can go ahead and talk about this. Probably isn't the hardest problem to have broken into a little group to try to work on. But I just had written down the equation from the previous page. So we're going to take our Fahrenheit temperature, subtract 32, multiply by 5/9. I get 37.0 degrees C. You may have known, if you know the two scales, about 37 is standard body temperature, in Celsius, and then we add 273.15 to the result, and we come up with 310.2 in Kelvin. So about 298 Kelvin's room temperature, and our body temperature about 310.2 Kelvin. Now, we should probably talk at some point, and it's going to be our next topic of discussion, of like why it is we might round these values the way we did. And so that's going to get us into the next topic of looking at units and looking at significant figures and figuring out how to round off results of measured quantities. Okay, so before we get there, why don't I throw another quick problem at you guys, just on making sure we can convert from one set of prefix units to another prefix. So maybe we know there's 100 centimeters in a meter. Maybe we know there's 10 to the 9 or nanometers in a meter. But how do we do this conversion? So maybe take a minute on this one and try to do this conversion to calculate the number of nanometers and 0.025 centimeters. Okay, so let's talk about this one. So we have our nanometers that we're looking for. Now this kind of gets us into using dimensional analysis. This is technically the last section of the chapter, which we were talking a little bit about on Friday on how to use dimensional analysis. But whenever we're trying to solve a problem using that tool as a math tool, I always like to start with what we're looking for, so number of nanometers. Sometimes a problem's so simple, when we get to more complicated problems, if we don't just start with what we're looking for, it might make starting the problem a little bit trickier. And so when we get to more complicated problems, we probably want to make sure, start with what you're looking for. It helps us begin a problem. And then we kind of start then the math of the problem with whatever information we're given. And then we try to convert that information into what we're looking for. And so centimeters to meters, there's two ways to carry out this conversion. It doesn't really make much of a difference which one you use. I used the 100 centimeters in a meter. You may have then said, well, I thought we were talking earlier that it was 10 to the minus 2 meters in a centimeter. And both conversions are true, so obviously we can take 100 centimeters equals 1 meter. We can divide both sides by 100 and come up with the other conversion factor, that 1 centimeter is 10 to the minus 2, or 1 over 100 meters. So we can use either one of those two conversion factors and get the right answer. The key is really making sure we get the right sign on 10 to the plus 9 nanometers. There's a lot of the little thing and the big thing. So there's a lot of the little nanometers and the big nanometer. The thing that's really easy to do is to make this sign minus and not realize that we made a mistake. So there's not 10 to the minus 9 nanometers in a meter. That would make the nanometer really big. The nanometer is really small. So there's a lot of the small unit and the big unit. Of course, we can redefine the unit or write it this way, where we have 1 nanometer is 10 to the minus 9 meters. Either way, we should arrive at 250,000 nanometers. Now, did anybody punch this in their calculator and end up getting answer B by any chance? Did anybody happen to get B? Are they willing to be brave? One thing that's sometimes tricky in a math problem is how do you enter 10 to the 9 in your calculator? And if we haven't pulled out a calculator in a while and haven't thought about this, sometimes I've seen students do like 10 times 10e9. So sometimes I've seen students put this in their calculator where they do like 10 times 10e9, but that's like 10 times 10 to the 9, which would be 10 to the 10. So that might have led you to answer B if you use that mistake. The thing you would want to do in your calculator is either do 10 caret 9, obviously, or you want to do something like 1e9 if you want to use a scientific notation. That's actually how I do it, because that's an easy way to do a power of 10, is just to do 1 times 10 to, with the e button. So I might do 1e10, and that's going to equal 10 to the 9. So there's a few ways that you might enter this into your calculator. If you got the minuses, then we probably just flip the signs on our problem somewhere along the way. Okay, so that's just a problem where we're using two of the metric conversions within the same problem. Also, you may have gotten stuck at first thinking, okay, how do we convert centimeters and nanometers in one problem or in one step, and breaking into 2 steps, I think makes this problem a little easier. Okay, so let's get into this topic of significant figures, where this is going to be how we round off our results. And so all the digits in a measured quantity, including the uncertain digits, are what we call significant figures. What this means is when we see a value like 25.5 meters, and we're assuming that this came from some sort of lab measurement or some sort of device that gave us this measurement, that this last digit is the uncertain digit, meaning that this digit carries some inherent uncertainty. If this digit were completely certain, then we probably would have had another digit after the 5, and then that digit would have been our uncertain digit. What this is really getting to is usually when you're making some sort of a measurement, you see maybe your object is in this range here, where you're looking at this on your device saying, okay, between this being 25.4 and this being 25.6, that this looks to be about say 25.5. That you're always interpolating, usually on a scale of where the device or where the object you're trying to measure happens to fall between like the notches on a ruler. The video I want to play in a minute kind of has this shown for us on how we can use different types of rulers or different types of measuring devices to get different precisions. Like if we had more notch markings on our scale, maybe we could have gotten another digit onto our measured quantity. But we didn't. With the tool we were using, we came up with 25.5 meters as the length of some object. Now, that last digit's what we call the uncertain digit. That's the one that had some uncertainty. That's the one that you're going to argue about. That's the one where you're saying, well, it's somewhere between 0.5, halfway across, maybe a little less, maybe a little more. This is the digit you might argue about in the result being right or wrong. Okay, but it's still a significant digit. I look at this quantity here, the entire digit, I say I have 3 sig figs, 3 significant digits, or 3 significant figures relating in that quantity. The more figures, the more significant figures a value has, the more precise it is. Like if we had this object, its length determined to be 25.532, let's say, meters, the difference between those two values, I would say, is just the second one with more digits is more precise. Because it has 5 sig figs. It's 5 significant figures. And the 2 here would be its uncertain digit. So that's a digit we would have been arguing about being 0.1 or 0.3 or having some inherent uncertainty in that digit. So when we're rounding calculated numbers, we pay attention to the significant figures so we don't overstate the accuracy of our results. When you throw a calculation in your calculator and you get like 10 digits on the screen of your calculator, those probably aren't all significant. We need to figure out where to round that calculation off to. So we need to make sure we're not overstating the preciseness of a result so we know when we're doing calculations where to round those calculations off. Okay, so here's this demo here. And I've done this in person, but the video is usually shorter, so let's see this. And this is also somewhat interesting because our preparations, Angie, she's the one who brought the hydrogen balloon out on the first day that we blew up. Friday was her last day, so she'd been with the department for 13 or 14 years, and so it's going to be a sad moment seeing her on the video on the very first day that she's gone. But here's this video that she prepared a while ago on the difference of different types of scales and what they mean in terms of measured quantities of an object.
use of a ruler can impact the significant figures?
I wanted to stop it just before there. And so if you were looking at the 9.6 measurement and saying, well, I thought it was 9.5, or maybe you thought it was 9.7, you can kind of see what we mean by there being some uncertainty because we're interpolating between the scale. Especially with the 9.75, if you actually look, I think you might have a little bit of an argument over, is that, should be 9.5 or 9.75, 9.76. Maybe you're looking at it differently than what somebody else would have looked at the screen and determined that length to be. The key is that we're interpolating between the scale markings. Or the balances we use, you've seen this in the lab. Did you guys weigh out some masses on the first day of lab? And the scale's going up and down on that last digit? That's because it's trying to interpolate that last digit too. So if your device is capable of interpolating that last digit, you want to get that last digit. It has some meaning. Like, I think the 5 is more meaningful than, say, this being a 0 or a 9. If you're looking at the scale, I think you can see, well, it's not quite that close to the next marking for 9.8. It's not that close to 9.7. It is somewhere in between. So there is some value in keeping that value as 9.75 and keeping it with the value. So it has some significance. That's why we include the value. But I think you can also see that depending on what device you use, if you had a length of, say, 9 or 10 centimeters for this object versus 9.6 centimeters versus 9.75, that the preciseness that you had recorded the object will determine how precise maybe you could determine its density. Like, let's say we determined the mass of this object, and we were trying to work out with the dimensions of the unit what its volume was by doing like a length times width times height or something, that the preciseness for which we determine the length, the width, the height, they're going to impact the preciseness we know the volume. That's going to later impact the preciseness of the density. So if we can more precisely determine a lab value, it will give us more digits. Then when we do a calculation, we should be able to round that value to a greater preciseness with more significant figures. Okay, so let's think about a couple of problems. Sometimes one of the tricky parts of significant figures is there's some numbers we're going to encounter that aren't lab measurements. Like when we're talking about taking an object like that bar and determining its length, that's a lab measurement. But when we're doing other things like counting objects, we can count objects very precisely or exactly. So let's do a thought problem. So what's the difference if I were to count every person in this room, and let's say I came up with a count of 300. Oddly, this class is a little smaller than last year. We actually had about 330 students, I think, last year. This semester, we're only at about 225-ish in the class, so a little smaller this year. But if we counted every single person in this room and the doors were closed, we knew nobody else had come in or left the room, and we count that there's exactly 300 people in the room. And we triple check the count. We use one of those counters so we make sure that we're not screwing up our counting. And there's exactly 300 people. How many sig figs does the number 300 have? And on the sort of, writing 300 people? I would say infinite. This is an exact quantity. So if this is an exact quantity, then it would mean infinite sig figs. You're going to see in a minute, if I just said 300 grams, you have an object that's 300 grams. Now we're shifting into that value being some sort of lab measurement. Anytime you're seeing something with a unit like meters or grams, we're assuming that somebody did this measurement in the lab. And this is actually going to be something we look at and just call 1 sig fig. We're going to say this value here is just has 1 sig fig, meaning the 2 zeros aren't really significant. If they were, I would have probably written this some other way. I may have written this as, say, 3.00 times 10 to the 2 grams, which we would interpret that way of writing this value as having 3 significant figures, where all these 3 are significant. Now, you may be saying to yourself, what difference does it make? Well, it makes a difference in just how precise we're treating the 2 values and how we might carry out the preciseness of the calculation with these quantities. With 1 significant figure, what we're saying is that this is our uncertain digit. If we write 300 grams, it means we're using a really poor device that was, when we had this object on a balance, it was like teetering between 100 teetering between 200 and 400. So it's like going back and forth, oscillating between 2 and 400. We're like, it's about 300. And we determined it to be 300. And the object could have been 315, the object could have been 285, the object could have been somewhere really vastly well between about 200 and 400 grams. But then when we use a different device, or we know that the mass is known to 3 sig figs, that this is like saying it's 300 plus or minus 1, or that the uncertainty is coming in that third digit of the value. So 300, if we had the object on a balance, this would have been teetering between 299 and 301. And so if we're thinking of a balance going back and forth, between about 299 and 300 for 3 sig figs, between 400 and 200 for 1 sig fig. And then when we do calculations, we might round them differently for those two values. So now if we did a different thing where we try to estimate how many people in the room, and we say, okay, there's about 300 people here, let's say. Well, that's an estimation now. How good can my estimation be? And I may think, to myself, am I good to the nearest 100? Am I good to the nearest, 10? Am I good to the nearest 1? And my ability to count probably isn't very good, so my counting ability is probably about plus or minus 100. So if we're estimating, we have to think how well can we possibly have estimated. If we're using some measuring device, what is its preciseness? Okay, so let's just think about significant figures and start thinking how we would count the number of significant figures there are in a given quantity. So 12 counted eggs. We have a dozen eggs. We have exactly 12 eggs. I can count them very easily. And so this would be an exact quantity. Infinite sig figs. Do you see how that 12 counted eggs is different than like 12 grams? Like 12 grams could have been 11, somewhere between 11 and 13. 12 counted eggs is exactly 12. So when a value is exact, we're going to treat calculations a little bit differently than when it's some sort of measured or inexact quantity. So 12 counted eggs, exact. Now, if you said you had a shipment of, 1,200 dozen eggs arriving, how many eggs do you have? Then you would say, okay, some are going to be broke, you're not going to have exactly, so you can start thinking that on big scales it's going to be really hard to count, but on small scales we can count precisely. What about having 105.0 liters of water? How do we look at this digit here? Well, anything after a decimal point is significant. So whenever I see anything after a decimal point, especially a 0, we count that digit as being significant. So all 4 of these digits are significant. So what digits are significant in a value? Well, obviously all non-zero values are going to be significant. If we have like the 0, sometimes, at first glance you may be like, well, is that 0 significant? Well, of course it is. That's no different than if it were a 1 or a 3. That value is significant. And if it's after a decimal point, we wouldn't have written it if it weren't significant. So it has to be significant after a decimal point. So that value there has 4 sig figs. What about these leading zeros here? Are they significant? They're not going to be significant. They're just like holding the placeholder for where the significant digits begin. So this digit here begins with the 3. We have 3 sig figs in 0.0305 grams. Now, one little trick should be if you take a value and just convert it to scientific notation, if we were to write this as 3.05, keeping all those, significant digits intact, and then times 10 to the minus 2 grams, that if you're writing a digit in scientific notation or regular notation, they should agree in sig figs. And so this, of course, I think we'd agree should have 3 sig figs. Last one's kind of tricky. It's a burette reading. Did you guys still do some burette readings in the first week of lab? If not, you might do them this week. So a burette is, it's a device that you can withdraw liquid from. So it has scale markings. It has a valve you can open, withdraw liquid from it. And so what you usually do is you're taking the before and after volume in the burette so you can figure out how much volume of liquid you're delivering. But now here, let's zoom in a little bit. That meniscus is right at the bottom of 20. Now, if I just write this as being 20 milliliters, do you see how that's kind of understating how precise we know that volume to be at that mark? So, in fact, if I wrote 20.0 milliliters, I'd say I'm still understating the value. Because if it were a little bit higher, if it were like right here, I could tell that that would be 20 point, and let's make sure we notice that this is 19 and 21 here. So these are 0.1 milliliter markings. So if I see the value about halfway in between, that would be about 19.95 milliliters for this measurement here, meaning I'm good to about 4 significant figures. So I should be writing this as 20.00 milliliters. So usually when you use a burette, you get 2 digits on your volumes, as long as you're careful to interpolate between the scale markings. Now when you do this in the lab, this is really small. Sometimes I bring my reading glasses to class, I forgot today, but this is a time in the lab, if you happen to have reading glasses, I doubt many people need those yet in the room, but if you do, I would use them for reading a burette, because it's really hard to see the scale markings of a burette. One other thing that you can actually do is kind of neat is if you just can't see, because like if I had to look at a burette, it's so hard for my eyesight to see that without glasses on. I could just take a picture of it though, zoom in very easily. So if you're in the lab and you're doing an experiment where you need to get a burette reading precisely, just take a picture of it, zoom in. You can see those scale markings very easily to see how you can get those extra significant figures. So about 4 significant figures on a burette reading. Okay, now, once we know some significant figures, we can start thinking about how we're going to carry out calculations when we're dealing with these measured and inexact quantities. And again, it's kind of important to kind of come back to the point is that we're trying to deal with calculations with these measurements, these inexact quantities, and we're not trying to rewrite mathematics. So like when you see ordinary mathematics, you can just know that the mathematical answer is all the digits. Like when you do, whatever times whatever, when you're not looking at these inexact quantities, the real mathematical result would be the full numerical result of all the digits being attacked. It's just whenever we have these measurements or inexact quantities that we're dealing with that leads to these scenarios of trying to round off our results. So the least certain measurement or inexact quantity is going to be the limiter on our significant figures in our result. So if we're just thinking, whatever, if we're taking 3 measurements, throwing them into a calculation together, imagine doing a length times a width times a height, where for whatever reason you made the length measurement really precise to a lot of digits. You made the width value very imprecise with a different scale with a different ruler, and then you made the height one with some other tool. The worst tool that you use is going to be the delimiter. It's going to be the one that's going to lead you to round to the fewest significant figures. So when adding or subtracting, so let's try to separate our math functions into kind of rules that we're going to apply for whether or not we're adding or subtracting versus multiplying or dividing. Adding or subtracting, the results are reported to the same decimal place as the value with the greatest decimal place. And let's think of an example of this in action right away, what we mean by decimal place and what we mean by being higher or lower. And so let's look at this calculation here. And so when I'm talking about rounding to the value with the higher or greater decimal place, I'm meaning closer to the decimal point or greater in numerical value. So I'm looking at the 0.05 being greater in numerical placeholder value than the 0.4140 ending in the 10,000ths placeholder. So what I'm looking at here is when I do this math, I'm looking at my placeholders. I'm going to line the decimal points up right on top of each other. And then when I carry out this arithmetic, it's probably easy to do it by hand, but I'm going to throw it into a calculator. That my result, if I just write in the result, would be 129.46 and then 40. But the key is I want to round it to the placeholder or the decimal place that's greater in quantity. So here, I didn't have to count sig. We did a little bit of counting sig figs in the previous slide, and we've been kind of thinking about that all along. We don't actually ever in a math or addition problem just count sig figs and use the number of significant figures as the basis of our rounding. It's all about where the placeholders fall relative to each other, and then we round off to the value that's greater in quantity. And so this would go to 129.46 if we round this value here. And let's even from there take, oh, it actually is the next problem. Let's do something simpler, like 75 plus 75. And let's remember that the 5 is like our uncertain digit. So if we're thinking the idea of 75 grams means our uncertainty is like 74 to 76, and the other value is also about 74 to 76. We add these two values together. Obviously, we get 150. But the question is, well, where is your uncertainty? Is it in the 0 placeholder, in the 5 placeholder, and the 1 placeholder? I think we can agree it's not the 1. We're not somehow adding 75 and 75 with an uncertainty of about 1 in each of those values and coming up with like 150 plus or minus 100. So that doesn't sound right. The 5 also doesn't quite sound right either. That if we think of doing this calculation, it doesn't seem like our uncertainty is going to be like 10 or greater for the uncertainty in this result. our uncertainty is falling right in the 0 placeholder. You know, it's the same placeholder. In this case, our placeholder is the ones placeholder. That's the value that we round to or we report to as being significant. So in this result here, 150, I end up with all 3 of those digits being significant. Now let's talk about something else real quick and then consider the difference of this 150 grams being different than 150 grams encountered in some other context. Let's say in some other problem, you're reading a problem that says you have a 150 gram, object. How many sig figs does that object have? Like different contexts. It's not the 75 plus 75 result. This is you're just reading a problem that says you have a 150 gram object. How many sig figs should you consider that object having? Here I would say it should be 2. These zeros here are kind of tricky to know the significance of if we're not told more information. So if we see 150 without any context, we're going to assume that that's 2 sig figs and that last 0 is just there to be a placeholder, and that it doesn't mean 150 plus or minus 1, it means 150 plus or minus 10 with 2 sig figs. Now, how could you know in a problem that 0 was significant? Sometimes you might see the 150 written this way where we put the decimal point after. So sometimes you'll see that to imply that all 3 digits are significant. But the best way would be if the problem wrote it in scientific notation. So if you use scientific notation, you can say 1.50 times 10 to the 2 grams if you want to imply 3 sig figs. Okay, so if you're encountering 150 in a problem, probably 2 sig figs, maybe a decimal point, not the best way, but a way that you'll see in some problems occasionally, trying to tell you it has 3 sig figs. If it had 4, obviously it would just be 150.0 and be really easy to determine. And then with scientific notation, if it's 2 or 3, we can write 1.5 times 10 to the 2 or 1.50 times 10 to the 2, depending on 2 versus 3 sig figs. Okay, now the reason why I wanted to kind of contrast that kind of nuance and that little trickiness with the digits ending in 0 is when we do a calculation and it happens to end in 0. It's a little bit of a different context. When we do 75 grams plus 75 grams, our calculator says 150. Our instinct's going to be, well, that has 2 sig figs because we just said this has 2 sig figs. If 150 grams in a problem has sig figs, anytime I see 150, it should have 2 sig figs. No, that's not the case. We have to look at our multiplication rule. We round to the placeholder. We round to the decimal place. We round to the 0's decimal place because it's the same decimal place that the 75 and the 75 values ended in and their significance. And it's also, if you think about the low end, the thing about one of the objects being really 74 grams, then our mass of the object, when we add these 2 masses together, would range from about 149 to 151 grams. So our plus minus is about 1 or 2 values. So we see our uncertainty falling in that 3rd digit in 150. So we might write this, if we had to write this down, as 1.50 times 10 to the 2 grams. So if we're reporting the value of this object, we might then report or use scientific notation to report the value. Now when we do subtraction, the same rule applies here. So we're just looking placeholders, decimal places, and so we're just rounding off here. Again, they both have values to the hundredths place, so the result here should be rounded to the hundredths place. So 125.6 minus 105.59 should be good to 20.01. So we have to make sure if the value ends in a 0 that we think about where the digit actually lies in significance. And if it doesn't end in 0, we still have to think of where we round to here, 20.01. Okay. Now, let's look at the multiplication and division rule. So when multiplying and dividing, here we count sig figs. And in a way, I think multiplication and division is very easy. The only problem with multiplication and division is once we see the easy rule, sometimes we're going to apply this to then adding and subtracting. We got to remember adding and subtracting has their own sig fig rule. So when we multiply 75 times 75, that's 5625 meters, just throwing into a calculator. So 75 times 75 has this answer. But when you do 75 meters times 75 meters as some sort of inherent lab measurement of these values, then we have to count sig figs. So we're not changing arithmetic, we're just dealing with arithmetic of these inexact quantities. 2 sig figs times 2 sig figs. When multiplying or dividing, results are reported with the same number of sig figs as the value with the fewest sig figs. So they each have 2, So the result should be reported to 2 sig figs. So 5,600 square meters. So we round that down to 5,600. Not changing arithmetic, but just rounding this off to how precise we can know this result. We could write this as 5.6 times 10 to the 3 square meters if we wanted to be unambiguous, but 5,600 should be interpreted if you write it that way as 2 sig figs. And then what about when we do a multi-step problem? When we do multi-step problems, we just have to do the addition rule when we add, and then the multiplication division rule when we divide. So what about 7.5 plus 2.6? So how many sig figs does this result have? 2, 3, what do you guys say? So I get 10.1 grams. Do I round that to 2 sig figs, or do I keep all 3? Or do I add a 0 for some reason? We're not going to add a 0, but we're 10th place plus 10th place should be rounded to the 10th place. So we apply the addition rule. We don't count. We don't do 2 times 2 sig figs and round this to 2 sig figs. And then I'm going to divide this by 4.55 grams, and that should keep 3 sig figs. So I have 3 sig figs divided by 3 sig figs. This should result in a value with 3 significant figures. So when I carry out that math, and this calculator, obviously, if you do it on like iPhone or whatever, you get like a tremendous number of digits. Obviously, we don't want to write all those down. They're not, most of them aren't significant. This should go as 2.22 grams, and then per milliliter. I wrote grams here. This is really volume. 4.55's unit, and the problem was milliliters. So 2.22 grams per ml. Okay, now, there's a lot of ways sig figs go wrong. One is, the simplest way I've seen a lot of people look at this, they see 2 sig figs here, and they automatically round the result to 2 sig figs. Or they just, so sometimes we make a mistake. We just look here and say, oh, I see 2 sig figs. There's division in the problem. The result has to have 2 sig figs. No, we just have to be careful to apply the addition rule, sig figs first, count those number of sig figs, note what that value is, and then carry out the second step. So we just carry out our significant figure rules in the order of the sequences that we apply the arithmetic in the problem. Funny story just from this weekend. We were driving. My kids are 10 and 12, 10-year-old daughter, 12-year-old boy. And so we see a precision, it's called like precision heating and cooling truck. And so I don't know why, like it just caught my kids' attention. They just thought it was funny that precision heating and cooling. So I asked my kids if they knew the difference between precision and accuracy. And it was funny, my daughter started rambling off on weird things. And then anytime I would ask her, what's precision again? She goes, it's that heating and cooling company. So that's forever what she's going to think precision is. But my son actually knew. I was actually very surprised. I had no idea that they would have introduced the difference between these two terms already in like 6th or 7th grade. But precision is sort of how close do you hit the target in a row, or how close do you hit the same sort of value in a row. So if you're throwing darts, it's like every time I throw darts, I'm hitting like 111. And I'm not aiming for 111, but I'm very precise on hitting that 111, even though I'm aiming for 20 or the bullseye. Being accurate is hitting the bullseye when you're trying to hit the bullseye. So accuracy is hitting your target, how close you get to the target, or if you do a couple of measurements, how close the average comes out to your target. And the precision is how repeatable is your measurement. So you could have, let's say we're aiming at the bullseye. You could have good accuracy and precision where you hit the bullseye every time. So that's precise and accurate. Accurate because you're hitting the target, precise because it's repeatable. You could have poor accuracy. Let's say you're intending to hit the bullseye, but you're hitting, double 20 every time. Then that would be good precision because you're on point, but just not on the right point, so you're not accurate. And then you could be all over the place. You could have poor accuracy, poor precision. And so why does this matter? Why does the difference matter? Well, I think the reason why we talk about this is it has to do with why we might carry out multiple trials in the lab and why sometimes we do a couple of different trials with an experiment, because we're trying to see how repeatable our work is, and the technique is that getting a value that's hopefully repeatable. If we apply our lab technique properly in an experiment and we do like 2 or 3 trials, they should generally come out to be pretty close together. If one's far off, it probably suggests either we made a mistake probably on both trials or all three trials, or it might suggest that there's a problem with our procedure. So it helps us kind of test the procedure, test our skill, test the value for the experiment to be repeatable, and then usually we want to then compare that result to the literature value or the expected value to see if we were on accuracy, to see if maybe we were miscalibrated on something. It's possible we could be using a balance that's just giving us a high mass every time, and we don't even know until we kind of like compare it to what the mass is supposed to be and see we got 5 measurements all repeatable, all very much the same value, but nowhere near where they're supposed to be. So if we test ourselves with a couple of different trials, we can see how repeatable our trials are. If we then see how close they agree with some trusted result, we can then see how accurate our work was. And so usually we're trying to figure out with our lab work, was it accurate or was it precise, or hopefully both. Now precision to me is like sig figs. Precision is how many digits the value has. The more digits, the more precise. And then, so a mass of 5.25554 is more precise than 5.2. And then the accuracy is just how close it agrees with the value it was supposed to be. Okay, so to the proper preciseness of sig figs, we have an object that is 50 grams, 50.00 grams, displaces water in a beaker. So you use a beaker, you take water from the 75 milliliter determined volume up to 125 mils. What do you guys think the density is of this object? So let's write this out. So we have grams for our mass, our volume. So we just kind of ended up into a significant figure problem, kind of like the previous one we just did. How many sig figs does that result have? It's 50. Are all 2-digit significant, or is it just one? Again, this is that trick. If I said 50 milliliters of ethanol in a different context, you might say 1 sig fig. But in the context of this problem here, when I line up my values, we're significant out to the 0. So this has 2 significant figures. So we know something about that 0 in our quantity. We know it's significant. And then we're going to divide it into 50.00, obviously 4 sig figs. So our result should be rounded to 2 sig figs. What if we could determine the volume that this object is displacing more precisely? What if we use something better than a beaker where the markings aren't very easy to make a precise volume measurement? We could maybe use a graduated cylinder. So a graduated cylinder contains a volume, has more precise markings than, say, a beaker does. If we repeat this experiment and we use now a graduated cylinder where we can more precisely note the before and after volumes of our displacement, and then we also can reweigh the object if we wanted and determine its mass to be a little bit more precise using an analytical balance. So our volume, 124.0 minus 75.5, is now 48.5. With all 3 of those digits being significant. We kind of wasted our time here in the mass because we had 50.00 on the previous page, if you recall, using like a top-loading balance, perhaps. And here we have a more precise balance. We didn't really need to use a better balance because that wasn't limiting our result on the previous calculation. But this one here, dividing into the mass with a bunch of sig figs, we round to 3 sig figs. So we'd be rounding this off to 3 significant figures. So we would have improved the calculation of the density of this object by a significant figure by more precisely determining the object's volume. So how well we can determine that volume's, the volume of that object and how precise it is impacts how well we can determine the density of that object. Okay, so we've been using dimensional analysis a bit. We haven't really just had a slide on it, but this is our main way that we're converting units. It's how we were converting units at the start of class. It's also a good problem-solving technique. We're going to use this a lot throughout the semester. So you're going to see a lot of dimensional analysis problems. I want to do one of these cubic conversion problems next time. I don't want to end class with this one. But let's just start next time with this. Then we're going to get into chapter 2. There's a couple other sig fig problems at the end of notes. I'll put a video up to supplement, and it kind of even says in the notes that there's a few extra sig fig problems that we'll work on. I'll just put a video of these up after class in a couple hours if you want to see a few more sig fig problems. But we'll be into chapter 2 on Wednesday after one more problem from chapter 1. Have a great rest of your day. See you guys.